Hi. In the last class, we saw the basic connection, the basic relation between symmetries and conservation laws in quantum mechanics. We saw that the existence of a conservation law points to an underlying symmetry. Let's now start with our discussion on space-time symmetries and the related conservation laws. And first, we shall discuss the conservation of linear momentum and the underlying symmetry called the symmetry under displacement in space. First of all, what do we mean by space-time symmetries? Space-time symmetries are symmetries related to geometrical operations that you can carry out. This geometrical operation could be a displacement, it could be a rotation or an inversion. And inversion can be done in both space and time. An inversion in space is just a reflection at the origin. For example, you might have heard of the assumption that space is homogeneous. This means that space has the same property at different points, or space has the same property everywhere. So if space has the same property everywhere, then the physical behavior of a system should not change simply by translating it from one point to another. That is, if space is homogeneous, then the behavior of the system should be the same, independent of whether it's located at this point in space or whether it's located at another point in space. But if the physics does not change by translating the system in space, then we say that the system has a translational invariance. So we can say that homogeneity of space actually comes from a translation invariance or a translational symmetry. We can demand that the system does not change or the behavior of the system does not change under a translation by requiring that the Hamiltonian of the system is invariant under that particular displacement. In general, we can call a transformation a symmetry transformation if the Hamiltonian of the system does not change under that particular transformation. Now we shall actually see that a translational invariance actually implies the conservation of linear momentum of the system. So the conservation of linear momentum that we have talked about before actually follows from the homogeneity of space. It follows from the fact that space has the same property everywhere. Okay. Another assumption that we are familiar with is regarding the isotropy of space. Isotropy of space is the fact that space has the same properties in all directions. This means that the behavior of a physical system does not depend on its orientation. For example, you may calculate the period of a simple pendulum by letting it oscillate. It may oscillate in the east-west direction or in the north-south direction. If everything else remains the same, changing the orientation of the simple pendulum alone is not going to change its period of oscillation. This is possible because space is isotropic. So invariance under rotations has its origin in the isotropy of space. Now these geometrical symmetries are really very important. You can appreciate their importance by imagining a world where these symmetries do not exist. For example, you can imagine an experiment. For example, let's say measuring the cross-section of scattering, the scattering cross-section of neutrons by protons. First, let's imagine that this experiment to measure the scattering cross-section is being performed at two laboratories, one at Chennai and the other at Delhi. What do you expect in this situation? The general expectation is that if nothing else changes, all right, if everything else remains the same, except for the location of the two laboratories, then you are going to get the same measurement results. That is, within experimental errors, of course. The expectation that the location of the laboratory alone is not going to change the result is based on the presumption that the differences in the location and the orientation of the two laboratories have no effect on the outcome of the experiment. Similarly, we usually expect that repetition of an experiment will give the same result with an experimental error. You may carry out an experiment today and you may want to do it again tomorrow just to check. And if nothing else changes, you generally should get the same results. But this expectation again is based on homogeneity of time. That is, we expect that the experimental outcome is independent of the time at which the experiment is performed. And this is precisely what homogeneity of time means. Again, it's the homogeneity of time that allows students to check their seniors' record books to see if they are on the right track. Some people even copy the results from the previous years, maybe with slight modifications, And the instructor might not be able to find this out because people don't expect the experimental results to have changed. In science, reproducibility is very important. Right? Someone may claim regarding certain experimental results, but this cannot be verified until people at different locations and at different times actually verify this or reproduce the same experimental results under similar conditions. And this process is important. It's basic to all experimental sciences. And this is what permits the formulation of laws with the universal validity. Laws which are valid everywhere and at all times. So science works the way it does because of homogeneity and isotropy of space, and also due to the homogeneity of time. The evolution of science itself would have been very different if any of these symmetries was absent. Even in the absence of these symmetries of space and time, we might still be able to formulate general laws of physics. But you can imagine how complex these laws might become. For instance, such a general law would have to contain the information regarding how exactly they themselves change when we move from one point to another or from one point of time to another point of time. The life of a physics student would become much more difficult in that case, as you very well can imagine. So we are quite fortunate that these symmetries of space and time actually exist. Okay, now earlier we talked about how the experimental results did not depend on the orientation of the apparatus. Right? We said that independent of the orientation of the apparatus, we generally get the same results. But some of you might have immediately remembered certain experiments which crucially depended on the orientation of the apparatus. Examples are certain experiments involving magnets or magnetic needles or magnetic compass. The reason for this anisotropy, this looks like an anisotropy, right? Because you really have to arrange your experimental apparatus in a particular orientation to make certain measurements. And depending on the orientation of the apparatus, some of these results are going to change. Now, the reason for this anisotropy is not something fundamental to space. It is because on Earth, we are in the magnetic field of the Earth, which actually chooses a particular direction. So on the surface of the Earth, the north-south direction is actually special. Similarly, we know that the acceleration due to gravity is not the same everywhere on Earth. So for example, if we calculate the period of a simple pendulum, it can change from place to place, right? Because the acceleration due to gravity changes from place to place. This is actually an inhomogeneity. This is also a local effect. It is not, you don't have to attribute it to you don't have to think of it as an inhomogeneity of space itself. There is an inhomogeneity, but this inhomogeneity is because of an external cause and not a fundamental property of space-time. So in spite of these local anisotropies and inhomogeneities, we can still maintain that space is really homogeneous and isotropic everywhere. In any case, if space and time did not have these geometrical symmetries that we have been talking about, then the formulation of the laws of physics based on observations would have been a far more difficult task than it is now. Before considering each of these space-time symmetries in detail, we have to make a distinction between two types of symmetries. On the one hand, we have continuous symmetries, and on the other hand, we have got discrete symmetries. Continuous symmetries are associated with displacement in space and time and also rotation in space. These transformations are called continuous transformations because you can think of them as depending on a continuous parameter. In the case of displacement in space, this continuous parameter is just a distance. And for any value of this parameter, we have a possible transformation. We have a possible translation in space, which also means that you can translate in space by any amount that you like. Same is the case with time. In the case of rotations also, there's a continuous parameter. You could think of it as the angle by which you are rotating. And corresponding to any value of this angle, you have a possible rotation. And the discrete symmetries are those associated with inversion of space and time. These are clearly discrete. For example, think of a reflection. You cannot get a reflected image in general, by continuously transforming from the unreflected image. Now, the continuous symmetries that we talked about have universal validity, that is, they hold good for all known interactions. You know about the four fundamental interactions. There's the gravitational interaction, the electromagnetic interaction, the weak nuclear and strong nuclear interactions. The continuous symmetries that we talked about hold good for all these interactions. But the case of discrete symmetries is more complicated. For example, it is now known that space inversion invariance or symmetry under space inversion is not valid. It's not a valid symmetry in the case of weak interactions. This means that there are certain interactions whose mirror images or reflections do not correspond to actual interactions in nature. So certain interactions happen, but their reflected versions simply do not take place in nature. This is what we mean when we say that space inversion invariance is not valid in the case of weak interactions. Similarly, there are certain interactions whose time reversed version do not correspond to actual interactions that can be observed. So in that sense, time reversal invariance is also violated in certain reactions. For example, the time reversed version of the decay of neutral kaons has never been observed. With that long introduction, let us now move on to discussing the nature and properties of the operations that we talked about and also about the conservation laws associated with them. Let's start with the symmetry under displacements in space and the associated conservation law, the conservation of linear momentum. Now, there are two ways of describing a displacement in space. One way is to describe the displacement as a displacement of the coordinate system with the physical system fixed. All right, so let's say that we have a physical system and we locate it using a coordinate system. All right, and one way to describe a displacement is to think of the displacement as a displacement of the coordinate system. Right? So even if you change, if you shift the coordinate system to the left, for example, the coordinates of the physical system will change. So if the change in the coordinates of the physical system is due to the change in the coordinate system itself, then this viewpoint is called the passive viewpoint, or simply the passive point of view. You could also think of the displacement of the physical system. You could also describe the displacement as a displacement of the physical system with the coordinate system fixed. So in this case, we'll have a fixed coordinate system, all right, and we consider the displacement of the physical system in space in this coordinate system. In this case also, the coordinates of the physical system changes, all right, but this change is due to an actual displacement of the physical system. This point of view is called the active point of view. I hope it's clear to you that a displacement of the physical system through the vector rho vector is equivalent to a displacement of the coordinate system through minus rho vector. We say that these are equivalent because the new coordinates of the system are the same in both these cases. Let me explain. First, let's look at the active viewpoint. In the active viewpoint, we have got a coordinate system that is fixed. All right. Let's write the amount of displacement as rho vector, which is rho x I hat plus rho y j hat plus rho z k hat. So initially, let's say that the system is at the position x comma y comma z, and then it has been shifted to the point. Uh, let's say it has been shifted by an amount rho vector, right? So what are the new coordinates? The x coordinate of the system has now shifted to x plus rho x, and the y coordinate has changed to y plus rho y, and the z coordinate has changed to z plus rho z, right? These are the coordinates before. X, y, and z are the coordinates before the translation, and x plus rho x, y plus rho y, and z plus rho z are the coordinates after the translation. All right. This is the active viewpoint. Let's look at the passive viewpoint and a passive translation by an amount, passive change or passive displacement of the coordinate system by an amount minus rho vector. All right. So here also we have an initial coordinate system. Okay, and let's say that the coordinates of the physical system itself are x, y, and z. Now let's shift the coordinate system by an amount minus rho vector. Right, so the shifted coordinate system I have to draw now. Let me draw it just like this. Okay, Now, what's the x coordinate? The x coordinate, let's say that this is the x axis. So the x coordinate is actually this distance. All right. What's the new coordinate? This is the coordinate before the shift of the coordinate system. What's the new coordinate? The new coordinate is this distance. And what is this distance? It is the initial x coordinate plus the amount by which the coordinate system has translated in the x direction. So here also we see that the coordinates of this physical system go from x to x plus rho x, right? This is the distance x and this distance is x plus rho x. Similarly, y goes to y plus rho y and z goes to z plus rho z. We see that both in the active case and in the passive case, the new coordinates of the physical system are exactly the same. This picture shows the active viewpoint translation. Right here, the system has changed from the point P prime to the point P by a displacement delta rho vector. Right. So this is how we label the points. The point P, the position of the point P, the new position of the translated point. All right. This is denoted as R vector. This is the position vector of the point P. All right. The displacement was delta rho vector, and then the initial position vector can be written as r vector minus delta rho vector. Since the same displacement can be described either using the passive viewpoint or equivalently using the active viewpoint, we are free to choose either of the viewpoints. So this is the choice that we are going to make. We shall use the active point of view in the case of continuous symmetries and the passive point of view in the case of discrete symmetries. So if it's a displacement or rotation or even a translation in time, we imagine that the system itself is being changed or transformed. All right. A displacement would be the actual displacement of the system in space. A rotation would be the actual rotation of the system in space, keeping the coordinate system fixed. But when we discuss discrete symmetries, we shall talk about changing the coordinate system. So in that case, a space inversion would be equivalent to going from a right-handed coordinate system to a left-handed coordinate system. Coming back to translation in space. Translation in space is a continuous transformation, and all continuous transformations must also be unitary transformations. Can you think of why this has to be true? I leave that as an exercise. Earlier we said that a symmetry transformation is either unitary or anti-unitary, and it can be shown that all continuous transformations must be unitary transformations. So all these continuous transformations we are going to talk about, translation in space, rotation in space, or translation in time, these are all going to be unitary transformations. So space translation is a unitary transformation, and there has to be a unitary operator corresponding to this transformation. We already know that we can associate a Hermitian operator with any unitary operator. And this Hermitian operator associated to a unitary operator is called the generator of the particular unitary transformation. Let alpha hat represent the Hermitian operator, that is the generator of infinitesimal displacement delta rho vector of the physical system. So if alpha hat is the Hermitian operator and delta rho vector is an infinitesimal displacement, we can write the infinitesimal unitary operator corresponding to this displacement. We know how to write this. This unitary operator varies infinitesimally, or it differs infinitesimally from the identity operator. Right? It's very close to no transformation at all. And we have seen that this infinitesimal unitary transformation can be written as the identity operator minus I delta rho vector dot alpha vector hat. Since delta rho vector is a displacement, it's a vector. So the operator appearing here also has to be a vector operator. It should have three components. Now we have already discussed these translation operators in the first chapter. We are basically going to see exactly the same thing, but the presentation of the idea is a little bit different, that's all. Anyway, we start with this infinitesimal unitary operator corresponding to a translation in space. For now, we don't know what this operator is, which Hermitian operator this is. We have to find it. Let's now try to find out which Hermitian operator actually generates space translations. We shall work with wave functions, so the unitary operator corresponding to translations, all right, acting on the wave function, acting on the untranslated wave function, gives us the translated wave function. We shall denote the translated wave function with a prime. So psi prime of r vector is the translated wave function. Now we have just translated a wave function from the point P prime to the point P. For example, you can think of it like this. Let's say that the wave function had a form like this at the point P prime. Now we have just translated that entire wave function to the point P. We know that a wave function assigns a complex number to every point in space. But here we see that the value of the function at the point P prime, right, the value of the untranslated function at the point P prime is the same as the value of the translated function at the point P. All right, you can think of the height of this particular waveform, for example. In other words, the value that the untranslated wave function psi of r vector assigns to the point P prime is the same as the value the translated wave function psi prime assigns to the point P. Alright, so this statement can be written as psi prime of r vector is equal to, alright, so this is the value. Let's think of this as the point P. Alright. So let me write it like this. Psi prime, the value of psi prime at the point P, the complex number psi prime assigns to the point P is equal to the complex number that psi had assigned to the point P prime. Right? Because we have just shifted this thing to the right. Alright. So in general, we can write this like this. Psi prime of r vector, right, where r vector is the position vector of the corresponding to this point P. So we can write psi prime of r vector has to be equal to psi of P prime. The position vector corresponding to P prime is r vector minus delta rho vector. Alright, so we can write the action of this translation operator on the wave function psi of r vector is such that the function now changes to psi of r vector minus delta rho vector. In writing that relation, we have made use of the fact that the translated wave function psi prime, which is a different function of r vector, alright, at the point P after the displacement has to be the same as the wave function psi at the point P prime before displacement. We could also put it like this. If the original undisplaced wave function has a maximum at r vector, then the displaced wave function has a maximum at r vector plus delta rho vector. Just to make it clear, let's look at an illustration of this in one dimension. In this picture, this is the untranslated wave function and this is the translated wave function. Let's say that this function has been translated by a distance a. Note that the height of this wave has not changed. For a moment, let's imagine that this is a real function. Alright, so the value that this function assigns to the point x or x minus a is the height of this function at that point. Alright, you can ask what's the value of the function at this point. It's simply the height of this function at that point. Alright, you can ask what's the value of the function at x minus a, and that's just this height. Right? So when you translate this function to the right by an amount a, we see that the height of the old function at x minus a is the same as the height of the new function at the point x. Right? This is true for any point. This distance is a. Okay. You could also take some other point. Let's say this point. All right. At this point, the height is 0. So at this point, the value of the translated function psi prime of x is 0. All right. We see that psi of x also has a 0 value. All right. At a point corresponding to x minus a, if this is x, right, this distance, since this has been translated by a distance, if you take this point as x, then this point is x minus a. All right. So we can write this statement like this. The height of the translated function at the point x is the same as the height of the untranslated function, or sorry, it's the height of the untranslated function at the point x minus a. Or in other words, the value of the function, or the value that this function assigns to the point x, alright, the value that the translated function assigns to the point x is the same as the value that the untranslated function assigned to the point x minus a, right, which is in this case just the height of this function at that point. So this is what it means. In 3 dimensions, this would simply become psi prime of r vector is equal to psi of r vector minus delta rho vector. You could also write it like this. You can write psi prime of r vector plus delta rho vector is equal to psi of r vector. Means the same thing, right? The value that this function assigns to the point r vector plus delta rho vector is the same as the value that the old function, the untranslated function, had assigned to the point r vector. Okay, I hope this is clear. Now we have the translation operator acting on psi of r vector, right? This is the new wave function psi prime of r vector. Now we wrote this infinitesimal translation operator as the identity operator minus I delta rho vector dot alpha vector hat, where alpha hat is the Hermitian operator that is supposed to generate this particular transformation. Right? So let's write it in the infinitesimal form, and we get this as the identity operator minus I delta rho vector dot alpha hat acting on psi of r vector, and we just said that psi prime of r vector is psi of r vector minus delta rho vector. Okay. Now we can expand this right side in a Taylor expansion. Now you are familiar with Taylor expansions. If you have one variable, right? If you have something like f of x plus delta x, the Taylor expansion about the point x, you can make a Taylor expansion about the point, let's say x0, right? The Taylor expansion would be f of x0 plus f prime of x0 multiplying delta x plus f double prime of x0 divided by 2 factorial multiplying delta x square plus etc. Now, if delta x is an infinitesimal quantity, then we can just retain only up to the first order terms. Now, here we are dealing with infinitesimal translations, so we shall keep only up to the first order term. Right? But this is the Taylor expansion of a function of one variable. Right? You can easily generalize this to two variables. For that, you just note here that f prime of x0 is actually the derivative of f with respect to x, which is evaluated at x equal to x0. Okay. Now, if you have two variables, f of x0 plus delta x, comma y0 plus delta y, this is a function of two variables. And we are now making a Taylor expansion about the point x0, comma y0. So we have this term. This is f of x0, comma y0. All right. Plus, there are two first order terms now, right? Because this is a function of two variables. There are two first order terms. One would be the partial derivative of f with respect to x evaluated at x equal to x0 multiplying delta x. There's of course one more first order term, which is the derivative, the partial derivative of the function with respect to y evaluated at, actually we have to evaluate this as this at x comma y equal to x0 comma y0, right? And this is evaluated at x comma y is equal to x0 comma y0, right? Multiplying delta y. So there are two first order terms here. Now it's easy to generalize it to the case of three variables. In the case of three variables, there would be three first order terms of this form, right? Now what we have here is actually a function of three variables. So let's see how the Taylor expansion is of this function of three variables. Okay. For that, let me just write this like this. Psi of r vector minus delta rho vector means that this is written as psi of x minus delta rho x, comma y minus delta rho y, comma z minus delta rho z. Right? This is this x minus delta rho x and y minus delta rho y, z minus delta rho z. These are all components of this vector r vector minus delta rho vector. Now let's make a Taylor expansion. The first term is of course psi of x comma y comma z. Okay, and there are three first order terms now. So one is the partial derivative of psi with respect to x multiplying delta x. In the place of delta x, we have a minus delta rho x. So this would be minus delta rho x. The next first order term would be the partial derivative of this function with respect to y multiplying minus delta rho y, plus again there's a partial derivative of this function with respect to z, multiplying minus delta rho z. Okay. Now this can be written as psi of x comma y comma z minus, and let's pull this minus side outside, and inside we have the partial derivative of psi with respect to x multiplying delta rho x plus the partial derivative of psi with respect to y multiplying delta rho y plus partial derivative of psi with respect to z multiplying delta rho z. Alright, now we see that this is actually in the form of a scalar product of two vectors. One vector has components partial derivative of psi with respect to x, partial derivative of psi with respect to y, and partial derivative of psi with respect to z. These are the components of a vector which we call del vector psi, right? So what we have here, these partial derivatives that we have here are the components of this vector, all right? Dot, and we have delta rho x, delta rho y, delta rho z. All these are components of the vector delta rho vector. So what we have here is actually del vector psi dot delta rho vector. So we have this Taylor expansion. Psi of r vector minus delta rho vector is actually equal to psi of r vector minus, this is just a parameter, so let me write as delta rho vector dot del vector psi. All right, or we can pull this psi of r vector outside. Okay, and this becomes, here we have the identity operator minus delta rho vector dot del vector acting on psi of r vector. All right, this is the Taylor expansion of the function psi of r vector minus delta rho vector. Okay, now we compare it to what we had on the left hand side. On the left hand side we had 1 minus I delta rho dot alpha hat, alpha vector hat. All right, now comparing this, you see that alpha hat, right, alpha vector hat has to be, right, there's a minus sign here, there's a minus sign here also. Okay, but there's an I here, so what we have is I alpha hat, right, is equal to del vector. All right, or you can multiply by minus I hat, minus I on both sides, right? So this means that alpha hat is equal to minus I del vector. Okay, now we see that this looks like the momentum operator in the position basis, provided there's an h bar. So let's introduce this h bar in here. We can write this as alpha vector hat is equal to, alpha vector hat is equal to minus I divided by h bar multiplying h bar del vector. Okay, I have just multiplied and divided by h bar, right? So you see that this can be written as minus I divided by h bar, or let's write it like this, minus I h bar del vector is the position representation of the momentum operator, if you remember. So we see that alpha vector hat is actually equal to the momentum operator divided by h bar. We have again come to the conclusion that it's the momentum operator that generates a space translation. Right? The Hermitian operator that acts as the generator of space translations is actually the momentum operator. Okay, it's actually the momentum operator divided by h bar. All right. Since h bar is a constant, we can call this operator, the momentum operator, as the generator of space translations. Okay. Now we have identified the momentum operator as the generator of translations. Now we can write the unitary operator corresponding to the infinitesimal displacement delta rho vector as u hat subscript p of delta rho vector. Right? We put the subscript p here because momentum, we have found that momentum is the generator of translations. Delta rho vector is the parameter. Actually, it's a collection of three parameters because we are dealing with displacements in three dimensions. All right. So this is delta rho x, delta rho y, and delta rho z. So this infinitesimal unitary operator has now the form identity operator minus I divided by h bar delta rho vector dot p vector hat. Now this is the generator, or this is the unitary operator corresponding to an infinitesimal translation. You can also find the operator corresponding to finite translation or a finite displacement. So a finite displacement row vector could be thought of as a succession of infinitesimal displacements. So we can build up, we can take a large number of infinitesimal displacement operators like this and multiply them together to obtain a finite translation. And we have already seen in the first chapter, this calculation we have already seen in the first chapter. It gives us, if you combine an infinite number of infinitesimal translations like this, if you multiply an infinite number of infinitesimal translations like this, you get the exponential. All right. So we can write the unitary operator corresponding to finite translation row vector is equal to exponential minus I divided by h bar row vector dot p vector hat. If you don't remember how we go from here to here, please refer to the first chapter where we discussed the translation operator. So, the generator of translations in space is the linear momentum operator. And the unitary operator corresponding to translations we obtained as u hat p of row vector is equal to exponential minus I divided by h bar, all right, and row vector dot p vector hat, all right, where p vector hat is the momentum operator. Now, right up to now, we talked about the change of the wave function or change of state under a translation, all right. Now, just as we discussed the Schrodinger and the Heisenberg picture, we can equivalently talk about the change in the operator, change of the operator under this particular unitary transformation. And instead of saying that psi of r vector goes to u hat acting on or u hat acting on psi of r vector, we can equally well say that psi of r vector does not change and the operators transform in this manner. A goes to u dagger, okay, u dagger A u. Again, this is just a difference between the Heisenberg perspective and the Schrodinger perspective. It's now convenient to switch to the Heisenberg viewpoint, right? Because we say that a symmetry, we say that a transformation is a symmetry if the Hamiltonian is invariant under such transformations. So under space translation, the Hamiltonian goes from h to u dagger, right? U dagger h u. All right. Now, when does the Hamiltonian remain invariant? The Hamiltonian does not change if this unitary operator commutes with the Hamiltonian. All right. If they commute, if these operators commute, then we can bring it to this side and then we see that h hat goes to u dagger p of row vector, u p of row vector multiplying h hat. Now by unitarity, this is equal to the identity operator and we see that h goes to h itself. In other words, h is invariant. When is h invariant? H is invariant if the unitary operator corresponding to the transformation commutes with the Hamiltonian. Okay. Now, what's this unitary operator corresponding to translations? It is exponential minus ih bar row vector dot p vector hat. Right, and we have a p vector operator in here. So, when we say that h commutes with this operator, this actually means that you can check this by looking at the series expansion of this exponential. All right. Now, this is possible if h commutes with the momentum operator. All right. So we see that the Hamiltonian is invariant under translations if the Hamiltonian commutes with the momentum operator. But again, from the Heisenberg equation of motion, we know that if the Hamiltonian commutes with an operator, if the Hamiltonian commutes with the momentum operator, then dp dt is equal to 0. All right, because the time derivative of the momentum operator can be written as, okay, the time derivative of any operator can be written as in the Heisenberg equation of motion. This is equal to 1 divided by ih bar, the commutator of p with h. If p commutes with the Hamiltonian, that means dp by dt is equal to 0. All right. So the relation which says commutator of P with H equal to 0 implies that the total linear momentum of the system is conserved. In other words, conservation of linear momentum of a physical system is a consequence of the translational invariance of the Hamiltonian of the system. Alright, so if the Hamiltonian of the system is translationally invariant, if it does not change under a translation, then we see that momentum is a constant of the motion. So conservation of linear momentum actually follows from the symmetry under displacements in space. Now the Hamiltonian itself has the kinetic energy term p square divided by 2m and some potential energy term in general, alright? And when you calculate the commutator of P with the Hamiltonian, the contribution from the first term is automatically 0 because every operator commutes with itself. Right? So this commutator boils down to the commutator of P vector hat with V of R vector hat. Now if V of R vector hat, if the potential actually depends on the position, then there will be this position terms in here and this commutator is going to be non-zero. So for invariance to work, we should have this potential independent of R vector, or the Hamiltonian has to be independent of R vector. So the translation symmetry exists only if the Hamiltonian is independent of R vector. And the Hamiltonian won't be independent of R vector if there is some external influence, an external field, an external force acting on the system. In other words, the system should be free from external forces for a momentum to be conserved. Right? This is the kind of statement that we have seen in classical mechanics, even in Newtonian mechanics. Right? We have said that if there is no external force acting on the system, then the momentum is conserved. To discuss symmetry, we just made use of the Heisenberg viewpoint, where the operators change and the wave functions do not change. Now you may ask, can we come to the same conclusion using the Schrödinger picture also? That is, by assuming that the wave functions change under translations but operators remain the same. And of course we can come to the same conclusion, but now we call a transformation a symmetry transformation if the same laws of physics apply for the untranslated state and the translated state. So if psi prime, the translated wave function, and psi obey the same equation, right, obey the same Schrödinger equation, then we can say that the transformation is a symmetry transformation. That is, the translational invariance of the system can also be expressed by saying that the transformed wave function satisfies the same Schrödinger equation as the untransformed wave function. Okay? That is, the laws of physics do not change by simply translating from one point to the other. Let's start with the Schrödinger equation satisfied by the untranslated wave function, and let's apply the unitary operator for translations from the left. So you have to do it on both sides, right? Now, since this is a linear operator, it does nothing to these terms, right? And there's no time dependence in it, so you can just take it inside the derivative. Right? So the left side becomes IH bar partial derivative with respect to time of psi prime of r vector comma t. Why? Because psi prime of r vector comma t is equal to u hat p of rho vector acting on psi of r vector comma t. Alright, so this up hat acting on psi you can write as psi prime. And the right side becomes up hat h, up hat multiplying h hat acting on psi of r vector comma t. Now we see that psi prime obeys the same Schrödinger equation as psi provided up hat and h hat commute, right? Because if this unitary operator commutes with the Hamiltonian, we can write this as h hat multiplying u hat acting on psi of r vector comma t, all right? And now again we use u hat acting on psi is equal to psi prime. So provided provided this unitary operator commutes with the Hamiltonian, then psi prime obeys the same Schrödinger equation as psi. Okay, and in other words, this is a symmetry transformation, right? So we see that psi prime is equal to u acting on psi is a symmetry transformation provided u commutes with the Hamiltonian. All right. Now, in the case of translations, the translation is generated by the momentum operator. So we see that the translated state also obeys the same Schrödinger equation provided momentum commutes with the Hamiltonian. And again, if it commutes with the Hamiltonian, if the momentum operator commutes with the Hamiltonian, then momentum is a constant of the motion. We have again come to the same conclusion that conservation of momentum follows from symmetry under displacements in space, or translational symmetry. We have discussed the first of the space-time symmetries, which is the translational symmetry. Right? So we say that a system has a translational symmetry if the system does not change, right? If the Hamiltonian does not change under a translation. And if a Hamiltonian does not change under a particular unitary transformation, then the generator of that unitary transformation is a constant of the motion. In this case, if the Hamiltonian is invariant under a translation, then the generator of that translation, which is momentum, is a constant of motion. We see that momentum conservation follows from the homogeneity of space, or translational invariance of systems. So with that, let me conclude this class. I hope you have understood. Thank you.